Welcome back to Physical Science. It's great to see you again. So, today we're going to start talking about Chapter 9. Chapter 9 deals with atomic physics, which I understand it sounds super scary, but I promise this is not a bad chapter. It has very little to no math. We're going to do a little history. We're going to see how some ideas have developed over the years, and then we'll implement a lot of what we're going to talk about in this chapter in the next chapter. We'll see how it's actually going to be used. So let's get started. Up until the probably early 1800s, everything that we have talked about, or everything that was talked about, dealt with what was called classical physics. So, classical physics, sometimes we call it Newtonian physics because Newton had a lot to deal with developing a lot of the laws in this area. In fact, isn't that Newton down there underneath the tree? Now, you've heard the story. An apple falls out of the tree, and based on the fact that the apple falls, he starts to get the idea of gravity and starts to figure out why things happen the way they do and to try to find that relationship, that law that he can present that's going to give a mathematical description of that observation. Now, everything for that particular part, this is the stuff that's been studied for years and years and years. So we're talking large scale observable events. So what happens with a cannonball or an apple, or why do the planets move the way they do in the solar system? That's classical physics. Sometimes we refer to this as macroism. So macroism is something on a large scale. So this contains the parts of physics that we've covered previously. So we're going to talk about mechanics and how things interact with one another, waves, sounds, optics, electromagnetism. Then it starts getting into some kind of, I don't want to say gray areas, but a little more hard to explain areas. So at that point in time, scientists were realizing they couldn't use the physics, the knowledge that they've used up to this point to explain the new things that they were learning. And that's why we end up with this this new area. So we have atomic physics, quantum, nuclear physics. You're going to hear several different terms. Sometimes people use them interchangeably. Sometimes we refer to this as submicroscopic. So these are going to be things that you can't see in a normal microscope. They're actually smaller than that. But this is going to be our modern physics. So we have quantum physics, which is going to deal with the atom. Atomic physics deals with electrons and kind of how they move around in the atom. And then nuclear physics, we're going to focus specifically on the nucleus and see what happens. So we're going to talk about like nuclear power and bombs and all sorts of cool, kind of fun stuff, radioactive decay, that type of thing. A lot of times these terms are used interchangeably. I'm not too worried about that part. Just know that the rules of what we learned before aren't necessarily going to apply well to this new area. Now, this new area is going to lay the building blocks for our modern chemistry understandings, which we get to cover in the next unit, which I'm excited for. So let's go ahead and start that quick history lesson that we're going to start with. Now, to start this, we're actually going to go way back in time. We're going to go back to about 400 BC, and we're going to talk about the Greek philosophers. Now, remember, these were people who would sit around, they would discuss a problem, debate it. They're very philosophical, but they themselves did not do the experiments. So they didn't go into the lab and try things out. They just discussed the theories of why things happen the way they do. Okay, so one of the debates they had was over whether or not matter was discrete or if it was continuous. Here's what that means. Imagine I have a bar of gold and I have this perfect knife that will cut through anything. And I take that bar of gold and I can cut it in half. Put one of those pieces down and I cut the remaining part in half again and again and again. And I keep going smaller and smaller and smaller and smaller. Is there a point at which you can't cut it apart anymore? That there's something there that you cannot destroy or cut apart? Or does it keep going and going and going? So, the first one we want to talk about, that's Democritus right here. He said that matter was discrete, or that you're eventually going to get to the smallest point and you can't cut it apart anymore. Now, he called that smallest part atomos, but he wrote it in Greek and spoke in Greek, so it probably didn't look like that, but that's kind of where the idea of the atom comes from. Now, Aristotle and Plato came after this. They were in the belief that matter was continuous, where you could keep going smaller, 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 and there's no endpoint in sight. And they said, oh my gosh, you believe this silly idea that matter is actually discrete or has these what we call indivisible parts? That's just crazy. That's heresy. That's belief against God. We're going to throw you in jail. And so the idea that matter was continuous lasted for the next 2,000 years. So what happened 2,000 years later? So about 2,000 years later, in 1808, 1807, early 1800s, we have an English scientist by the name of John Dalton who comes along with what's called the billiard ball model. Now, a couple of things, very important things that he does. He provided proof that atoms exist, that we have something that's indivisible. You get to a smallest point and you can't cut it apart anymore. Now, where have you heard that term indivisible before? I know sometimes it takes us a minute. What about that one nation under God, indivisible in the Pledge of Allegiance? I wasn't a very smart child. I have very, very blonde moments as a child. And I think that, I don't know, I guess I thought for a long time it said invisible because there were invisible boundaries. I don't know. Like I said, I wasn't the most brilliant child in the world. But let's talk about what indivisible means in that part. Now, I know it does not seem like this in today's climate that America is indivisible. But I think the best example that I have of this, as sad as it is on September 12th, 2001. Now, I know it's probably before you were born, but on September 11th, we had a tragedy. That was, of course, when the Twin Towers were hit by planes, by terrorists, and the towers fell. It was a very, very sad day in America. But on the 12th, there were American flags flying everywhere. And all of a sudden, all Americans had a common enemy. And we banded together. So that's what we mean by indivisible. It's something where you can't break it apart. Now, unfortunately, America doesn't necessarily seem like that right now, but that's for another class to talk about. Just think of indivisible, where you have something you can't divide. Now, in this case, we're talking about the atom and how you can't divide the atom into smaller pieces. Now, today we know, there's protons, neutrons, and electrons, but you can't break apart the atom without losing the identity of that substance, of that element, or whatever it is you want to look at. Now, John Dalton believed that these atoms were featureless, they were indivisible spheres of uniform density. So all atoms looked identical to one another. They might be different in sizes, but they didn't have anything special about them, and they had this uniform density. And it's called billiard ball model because it was like the billiard balls. It's like pool balls. So if you've ever played pool before, all of the balls are the same size. They're all kind of uniform. They're just painted differently. So that's kind of the idea that John Dalton had about these different the atoms, that he provided proof again that they existed. So he said each chemical element is composed of small indivisible particles called atoms, which are identical for that element, but different for atoms of different elements. So silver atoms and gold atoms are going to be different from one another, but all gold atoms are going to be like all the other gold atoms. So, fast forward about 90 years to the late 1890s, we have someone by the name of J.J. Thomson, Joseph John Thomson. He comes up with what's called the plum pudding model. Now, have you ever heard of plum pudding before? I mean, it's like in some nursery rhymes, right? Well, what it is a pudding with raisins in it. So think of that as our model of what this one is going to look like. So the important thing that JJ did here is that he discovered the electron. He discovered that there was something negatively charged in an atom. And so he compared these electrons, these negative charges, to the raisins, while everything else was positively charged. Now, how he came about this particular theory um, model was he was using what's called a cathode ray tube. So on this one, we have a negative and a positive part, and then we had a stream, a ray coming out of it, which turns out this ray is actually a stream of electrons, but they really didn't know what it was. And so what he tried to do was deflect or cause that stream to move in some way. And what he found is that it was actually attracted to a positive plate. So if it's attracted to something positive, then it has to be negative. And so that's how he gets up with this idea that there's something negatively charged in the atom. And if there's something negatively charged, you got to have something positively charged. Now, JJ is also a very, very highly gifted teacher. 7 of his lab assistants, plus his son, go on to win Nobel Prizes. That's pretty impressive. All right, so let's see how they're going to change this model now. Now, one of J.J. Thomson's first grad students, actually his very first grad student supposedly, was this gentleman, Ernest Rutherford. He comes along and makes what's called the nuclear model. Now, he's born in New Zealand, he's one of the older kids, ends up getting a scholarship to Cambridge University, where he became J.J. Thomson's first grad student. So he's continuing on with a lot of this research that Thomson had actually started. Now, he goes on, he ends up doing a lot of research in Canada about radioactive materials, actually coins the phrases of alpha and beta decay, and does a whole lot of research in that particular area. Looks at the idea of half-lives, develops a method to show that the Earth was much older than what it was previously believed. But back to the idea of what we're looking at right here. He has what's called the nuclear model. Now, to figure this one out, he had what was called the gold foil experiment. Gold foil experiment. And that's pictured down at the very bottom. And so he has an alpha producer. Now, so he took the element polonium, and then he took that polonium and they had alpha particles come out of it. So we had a stream of alpha particles. And he had just a little bitty slit, so it would just have just a little bitty stream of those alpha particles. And he wanted to see what would happen when the alpha particles would hit a piece of gold foil. Now, around this, completely around this, they have this detector. So whatever would happen with those alpha particles, they could track that. Now, over on the far right, it shows what ended up happening. Now, if all of the atoms would have uniform density, all of those alpha particles would have done exactly the same thing when they hit the gold foil. They all would have been passed through, or they all would have been reflected off in some way. But that's not what happened. Um, what happened was actually really surprising. So it turns out that most of the alpha particles, when they hit the gold foil, went through them undisturbed. They just went straight through this gold foil. But some of them were deflected at a certain angle, and because they had that detector, they could actually see like how far that angle was. And then some of them almost bounced back. So it must be that those few rays that did something different, they must have hit something that was really massive. Now, massive in this case doesn't necessarily mean large. We're talking about something that has a very concentrated mass associated with it that's like solid. Um, so that's where we get this nuclear model from. So when those rays came in, that alpha particle, and they hit that something massive, they bounce back. But most of the alpha particles didn't hit that little massive part, so that massive part has to be really small. So how Rutherford actually described this is that you have, he called it a nucleus. Nucleus in Latin means like little nest, something like that. So we have something that's very massive but very small. And then all around that, we have this empty space. And that empty space is where the electrons are. We're not really concerned about what the electrons are doing at this point. We just know the negative stuff is on the outside, and in the center we have something that's very, very massive. Now, this just completely floored them for a while. They actually compared it to the effect of firing a 15-inch artillery shell. So imagine a great big bullet, and they shoot it at a piece of tissue paper. Now, you think it'd just go straight through the tissue paper, right? But then something happens, and it's reflected back and hits the gunner. This was how surprised he was at this particular information. Now, he didn't come up with this all by himself. He actually recalled an idea that was proposed back in 1904 by a Japanese physicist. But he actually provided proof. So, of course, we give the credit to Rutherford. Now, all of these guys have such a fascinating history when you go back and look. For example, Ernest here, he has an interest in golfing and motoring. So this is right when cars were starting to become popular. So if you can imagine, he's out there and, they would always have like the driving glasses and the scarf blowing in the wind, all of that good stuff. In 1914, he is knighted, and in 1931, he actually becomes Baron Rutherford of Nelson. Now, unfortunately, in 1937, he actually ended up with a really bad hernia, but because he had a title, because he was what's called a peer, he actually had to wait for a titled doctor to get there. And they think that delay was very detrimental for him. But that's what the nuclear model is. So now we have not is that the atom is uniform density, such as with a billiard ball. The plum pudding, we had a positive and a negative. We discover the electrons. And now we discover the fact that there's a nucleus, that there's something in the center of the atom that is very, very massive. Now, the ideas are going to come along even more. We have lots more to go over, so come back for part 2 to see some more.